Hello everyone. Now I would like to continue with the property of the discrete Fourier transform. For the property of the discrete Fourier transform, we will have the shifting property, modulation, folding, product, convolution, correlation, center ordinates, and the Parseval theorems. We will look at it one by one through the example. Example 4.6. Given the discrete Fourier transform pair xn equal to 1, 2, 1, 0 and the x DFTK is 4, negative 2j, 0 and 2j with the n is equal to 1, 2, 3, 4. Okay, 4. So first question is find the yn equal to x, n minus 2 and the DFT of the yn. If you look at the question yn equal to x, n minus 2. Okay, minus 2, you know that this one is the shifting. So this is the time shift property. Then you check on your table for the time shift property. For the signal of x n minus n naught, the x DFTK is the x DFTK exponent minus j 2 pi k n naught over n. So by following the time shift formula, we can substitute in the value. Okay, so we have the y DFTK equal to x DFTK exponent minus j 2 pi k. N naught is 2. N naught is referred to this one. This is the N naught. Okay, so it's 2 over 4. So we can simplify like exponent minus j pi k. Okay, minus j pi k. So now we can solve it one by one. So x DFT 0, the k is start from 0 to 3, okay, 0 to 3 because we have n equal to 4. So and then x DFT, okay, x DFT, you follow this formula, so x DFT k you refer to 0, right? So exponent 0. So now you have the x DFT 0, okay, this is x DFT 0, x DFT 1, x DFT 2, x DFT 3. So x DFT 0 that is equal to 4. So I have 4. The value is 4. Then x DFT 1. So I substitute the value of 1 for the k. And then exponent minus j pi k. K is 1. Okay. So exponent x DFT 1 is negative 2j. That is referred to the given x DFT. So this is minus 2j. And then cos the exponent negative pi j pi. Okay. So you can write down as cos pi minus j sine pi. So this is this is referred to the Euler Formula. Okay. So minus j2, this is minus 1, equal to 2j. Okay. And then x DFT2, that is equal to x DFT 2 exponent minus j 2 pi. Sorry, I shouldn't write x DFT. It should be the y DFT. My mistake, sorry about that. This one should be y DFT. This one also y DFT. This one also y DFT. Because we need to find the y DFT, not DFT. Okay. Okay, next is x DFT2. We'll have the 0, okay, based on the question given, that one is 0. And then exponent minus j 2 pi. So this one will give you 0. And next one is y DFT 3. That is equal to x DFT 3 equal to exponent minus j 3 pi. So exponent x DFT 3 based on the question given, that one is the 2j. So refer to 2j and then cos 3 pi minus j sine 3 pi. So this will equivalent to negative 2j. After you solve this one and you multiply with the 2j, you get negative 2j. So that's all for this time shift properties. Now we go to the next one. Next question is the z DFT k equal to x DFT k minus 1 and x inverse discrete Fourier transform of Zn. So if you check back the table, property tables, if you look at this one, the question is x DFT k minus 1. So x DFT k minus 1 is referred to the modulation. Okay, it's a modulation properties, and the xn is like this. Xn exponent j 2 pi n cannot over n. So we get the I inverse discrete Fourier transform. For the z DFT k is equal to x DFT k minus 1. So what is the z DFT k? Z DFT k, for the x DFT we have 4 minus j, 4 minus j2, 0 and j2. Okay, since it's a negative 1, so we must move the origin 1 unit to the left. So we have this one should be j2. Okay, this one is a periodic, so we move the back to the front. Okay, because the signal is repeated, keep repeated. So j2 4 minus j2 0, but we still remain the n equal to 4. So this is the z DFT k. And then for the inverse discrete Fourier transform of the Zn, we have the xn equal exponent negative 2 pi n naught k over n. Okay, this one is if refer to the example, that one is k naught. Okay, so this is xn, you substitute xn as exponent j2 pi k. So n will refer to the later on xn. Okay, xn will start from 0, 1, 2 and 3. For the k naught is referred to the 1. The k naught is referred to the question x DFT k minus k naught. So from the question there is the k minus 1. So that k naught is equal to 1. Okay, k naught is equal to 1. So this one I should write down is 1. K naught is 1. N is 4. So I have j pi n over 2. Okay. So now when n equal to 0, the z0 is equal to the x0, okay, x0, exponent j pi 0, okay, over 2. So this is x0 is 1, exponent 0 you also get 1. So you get the answer is 1. And then when n equal to 1, the z1 equal to x1 exponent j pi 1 over 2. So x1 from the question that is 2, okay, exponent j pi over 2. This is equal exponent j pi pi over 2, so you can use formula cos pi over 2 plus j sine pi over 2. So you get positive j. So this one equal to 2j. And then for n equal to 2, z2, that is the x2 exponent j pi 2 over 2. That is equal to 1. And then exponent j pi. So this is exponent j pi, you get minus 1, okay? Minus 1, so your answer is minus 1. So for n equal to 3, z3 is x3 exponent j pi 3 over 2. So x3, you will get the answer is 0. So the answer, you multiply with the exponent, also get 0. So now your Zn is 1, okay, 1, 2j, negative 1, 0. 1, 2j, negative 1, 0. So the origin is still at the value of 1. So that is the property of the modulation. Now we go to the next question. Next question is Gn equal to x minus n and x DFT. So x negative n, that one is referred to the property of folding. Okay, it's a property of folding. So for a property of folding, if you refer to a table, that is the x negative n and the DFT is x DFT minus k. So the folded signal of the xn is 0, 1, 2, 1. Okay, folded signal of the xn is 0, 1, 2, 1, and then the signal is repeated 0, 1, 2, 1. So where is my origin? If you refer to here is this one. Okay, this is the origin. So for the n equal to 4, so I will just take 4 sample. Okay, I will just take 4 sample. So the answer is 1, 0, 1, 2. So the answer is 1, 0, 1, 2, and the origin always at the first place. And then for the GDFTK, and then the x equal to x DFT minus k. So this is the property of the folding. So x conjugate of the DFTK. So this equal. So minus k is equal to the conjugate. Alright. So conjugate, if you refer to the question, that is 4 minus 2j, 0, and 2j. So it conjugate only at the imaginary part. So you will have the answer. The amplitude is still the same. For the negative imaginary part, you will get a positive. For the positive, you will get the negative. Okay? If you don't want to be like this, also can. Just that you need to do like just now, the folded version. Okay, or I can write it like, okay, the folded version of the x DFTK. So you write down from 2j, 0, okay? Okay, j2, 0 minus 2j, and then 4. So you repeat again, j2, 0 minus 2j, and then 4. Okay, so the origin is at here, so you have count the 4 sample. Okay, so this is the same answer with this one. You can either do in conjugate or is a folded version, also can. Now we next go to the fourth question. Question number 4, Pn equal to the x conjugate n and its DFT. So it's the conjugate properties. Pn equal to x conjugate n. So you will get 1, 2, 1, 0. But this one, Pn, no change because there is the imaginary part. Okay? Conjugate only works for the imaginary part only. Okay. So x DFT minus k. So x DFT. Okay, for x conjugate and negative k, so I have this one minus k conjugate. So I can have the x conjugate also equal to x conjugate DFT k because okay, and then this one also conjugate. Okay, I can change it. So x DFT is conjugate, so 4 minus, you conjugate, you get positive 2j, 0 and minus 2j. And then conjugate. So when you conjugate, you still get back the same value. This is the origin. Okay? So this means that since the PDFT equal to XDFT, this means the xn equal to the x conjugate n and imply that the xn is a real value. Question number 5, hn equal to xn times with the xn and xdft. So if you look at this one, xn times with xn, so this is the product pointwise. So this means is the product property. So hn equal to the xn times with the xn. So xn you get 1, 2, 1, 0. And then you product with the same 1, 2, 1, 0. So 1 times 1 you get 1. 2 times 2 you get 4. And then 1 times 1 you get 1. 0 times 0 you get 0. So this is the product pointwise. And then for the DFT, so hash DFTK equal to 1 over n x DFTK convolute with the x DFTK. Okay, if you check with the table, it's also mentioned like this. So this is the formula of the product properties. 1 over n x DFTK convolute with the y DFTK. So for this convolution, there must be a periodic convolution. Okay, so given the x DFTK is 4, negative 2j, 0 and 2j. So you can either use the wrap around or using cyclic method. So first of all, we need to determine the first index. So first index, okay, first index is 0 because left hand side nothing. For the right, for the last index, you have the 1, 2, 3 for the XDFT, and then you time with another XDFT. So 6, 3 plus 3 is 6. So first index is 0 and last index equal to 6. So this is you already studied on the previous chapter, that how to determine the first index and the last index. And then we can draw a table. We can draw a table for the K, 0, 1, 2, 3, 4, 5, 6. Okay, so this is the x DFT k. The value is 4 minus J2, 0, J2. And then next one also the same. 4 minus J2, 0, J2. Okay, so you can multiply. So 4 times 4 you get 16. 4 times negative 2j you get negative 8j x. Okay, 4 times 0 you get 0. 4 times 2j you get 8j. And then also you're starting from this one, negative j2 you times with 4 you get negative 8j. And then negative j 2j times with negative 2j you get 4j squared. And then this one is 0. And then you get negative 4j squared. Okay, j squared, not 2j, okay? And next one you get starting 0, so everything is 0. And then the last one, 2j, so 2j times with 4 you get 8j. Okay, 2j times with negative 2j you get negative 4j squared. And then 2j times 0 you get 0, 2j times 2j you get 4j squared. Okay. If you look at here, you have this is the j squared, j squared, j squared, j squared. So you can change it again. This 4j squared. So j squared is equal to negative 1. Okay. J squared equal to negative 1. So you can multiply in or substitute the value of negative 1. So you get negative 4. Similarly to this one, so you have negative 4 multiplied with negative 1, you have 4. And same to this one, you have negative 4, negative 1, you get positive 4. And this one, 4 with negative times with negative 1, you get 4, negative 4. So the total answer is 16. Okay, this is the summation, 16 minus 16j minus 4, 16j, 8, 0. Okay, this is 4 plus 4, okay. 4 plus 4, 8, okay. So this one is negative 4. Okay, so in order to solve this question, you must remember to change the j square into negative 1. So you get the value. So as you know, the n is equal to 4. So using the periodic wraparound method, so n is equal to 4. So first half, I will have the 16, negative j16, negative 4, and j16. So second half I have the 8, 0, negative 4. So and then I put a 0 pass, okay, and I sum up, okay, I sum up, I will get 24 minus j16, negative 8, and positive j16. So therefore my HDFTK is equal to 1 over n is equal to 4. So 24, negative j16, negative 8, and j16. So this will equivalent to 6. Okay, always remember the periodic convolution. First one is the origin. Okay, 6, negative 4j, negative 2, and 4j. So this is the answer. Question number 6, that one is the Cn equal to xn, convolute with the xn. Okay, so this one is the xn convolute with the xn. So we know that this is a periodic convolution. Okay, so xn is 1, 2, 1, 0. Convolute with 1, 2, 1, 0. So you will get, what is the answer? You can either use the wrap around or the cyclic method. So now I can use the just now we use the wrap around, now I use the cyclic method. Okay, for the cyclic method, as I told you just now before, is inside is a 1, 2, 1, 0 is the clockwise, you arrange as a clockwise, and then you have another circle at the outer circle, and then your value arranged is anti-clockwise. Okay, so you start with 1, 2, 1, 0. 1, 2, 1, 0. Okay, so now you can multiply. Okay, 1 times 1, okay, this is for the Cn, C0. 1 times 1, you get 1, plus with 2 times 0, you get 0, plus with 1 times 1, you also get 1, plus with 2 times 0, you get 0. So this is 1 plus 1, so it's equal to 2. And then second one, okay, you still remain, okay, inside inner circle no move, you only move the value of the outer circle. So remember it rotates clockwise. So just now the value is 1, 2, 1, 0. Okay, so I start now, I move it clockwise, so I move this one is 1, 2, 1, 0. Okay, so this is C1. So 2 times 1, 2 times with 1, I get 2, and then 1 times 0, I get 0, plus with 1 times 0, I get 0, plus with 1 times 2 is 2, so I get 4. Okay, and then next, inside the inner circle remain no change, so it's 1, 2, 1, 0, and outer circle the value clockwise. Okay, just now I start with here 1, 2, 1, 0. Okay, so this is C2. So C2, 1 times 1 you get 1, 1 times 0 times 0 you get 0, 1 times 1 you get 1, 2 times 2 you get 4. So you get 6. Then the last one, again inner value no change, and then outer value rotate clockwise. So this one is 1, 2, 1, 0. Okay, so this is the C3 equal to 0 times 1 you get 0, plus with 0 times 1 you also get 0, plus with 1 times 2 you get 2, 2 times 1 also get 2. So this one you get 4. Therefore your Cn is equal to 2464. Okay, 2464. And then for the CDFTK, if you refer to here for a periodic convolution, the XDFT is product with the YDFTK. This means that the XDFTK product pointwise with the XDFTK. So this is a product pointwise. Okay, this means that you product each point. So 4 times 4 you get 16, Okay, 4 times 4 you get 16. This one times this one you get 4j squared. Okay, 0 times 0 you get 0, and then 2j times 2j you get 4j squared. So this will equivalent to 16. 4 minus 1, 0, 4 minus 1. So this one equal to 16, negative 4, 0, and negative 4. Okay? So this is about the periodic convolution. Next, we look at the question 7. Sn equal to xn convolute multiply with the xn. But we also, this one is a convolute also. Okay, this one is a regular convolution. This is a periodic convolution. So xn convolute with the xn for regular convolution. For the xn convolute with the xn, so we know that this is the regular convolution. Okay, how do we differentiate between the regular or the periodic? If you look at this circle, there's no circle, just this one. This symbol is a convolution. Or with this one is a periodic convolution. Okay. So xn is 1, 2, 1, 0 convolute with 1, 2, 1, 0. Okay. The starting index is 0 because left hand side you don't have any, because there's a this is starting at first, this one also is starting at first value. So first index always has 0 and last index is 6 because 1, 2, 3, 4, 5, 6, so we have 6. So n start with 0 to 6. And then this is the xn and xn. So 1, 2, 1, 0. This is also 1, 2, 1, 0. So you keep multiply. Okay, you multiply. So 1, 2, 1, 0, and then 2 times 1, so get 2. So 2, 4, 2, 0, and then this is 1, 2, 1, 0, and the last one also 0, 0, 0, 0. When you sum up, you get 1, 4, 6, 4, 1, 0, 0. So your Sn equal to 1, 4, 6, 4, 1, 0, 0. So in order to find the xdftk, okay, so find the xdftk, we know that the n is equal to 4. And then the n plus n minus 1 is equal to 4 plus 4 minus 1, which is equal to 7. And then the xz n is equal to 1, 2, 1, 0, and then 0 pad. Since the n plus n minus 1 is equal to 0, so you 0 pad so that the length of the xn is 7. So this is 0 pad. So you have 7. 1, 2, 3, 4, 5, 6, 7. Okay? 7. So now the xdftk is equal to the summation n to 0 to 4 xn exponent minus j 2 pi n naught k over n. So you can substitute the value. So this one is the summation of the S0. I substitute the n equal to 0. So this is I want to find x DFT 0. So x DFT, the S0, E0, I substitute the n is 0. And then plus with when n equal to 1, this one is E exponent minus j 2 pi 0 over 7, because the n is 7. So this part I will get the plus with S2 exponent 0, because the k here is 0, so all the k you will substitute with 0, so that's why you will get exponent 0. Okay, then x4, x2, x3, this one also 0, plus s4 also 0. And then the value x0, x1, x2, x3, and x4 I obtain from here. Okay, I based on the result obtained from just now. Okay, 1, 4, 6, 4, 1. So I have the 1 plus with 4 plus 6 plus 4 plus 1. So total up I get 16. So this is the XDFT 0. For the XDFT 1, so again I will still have the x0 minus j2 pi, n is 0, okay, k is 1, divided by 7, plus with x1, okay, when n equal to 1, exponent minus j2 pi, and k is still 1, divided by 7, then plus with S3, exponent minus j2 pi n equal to 3, k is still 1. Okay, and then plus with S4, exponent minus j2 pi n is 4, k is still 1, divided by 7. So bear in mind that this is referred to the k value. This is the k value. Okay, so this one is the k value. And this one is the n, which is same as this one, the n. So next, I solve it, I simplify it. So 1 exponent 0, because this part is a 0. And then plus with 4 exponent minus j2 pi over 7. And then plus with x3 is 6 exponent minus j. This one is, where is my x2? I missed out my x2. S2 exponent minus j 2 pi to 1 over 7. So it's 4 pi over 7. And then plus with S3 is 4 exponent minus j 6 pi over 7. Plus x4 is 1 exponent minus j 8 pi over 7. So this one is 1. So this one I can solve using the formula. I change the exponent to a cos. So I have the 4 cos 2 pi over 7 minus j sine 2 pi over 7 plus 6 cos 4 pi over 7 minus j sine 4 pi over 7, then plus with 4. Okay, so this one is a cos 6 pi over 7 minus j sine 6 pi over 7 plus 1 cos 8 pi over 7 minus j sine 8 pi over 7. Okay, and then this is equivalent to, when you solve this one, I have 1 plus 4, 0.6235. Okay, this I already pressed the calculator and I get the answer like this. 6 minus 0.02225 minus J 0.9749 plus with 4 minus 0.9009 minus J 0.4339 plus with negative 0.9009 plus J 0.4339. So when I simplify all this, I will get the answer negative 2.3455 minus J 10.2783. So this is just for the XDFT 1. So then you can, same method, you can find the XDFT 2, XDFT 3, 4, 5, okay, until the end. And this is the answer. Okay, this is the answer for the XDFT case. So just now I have found the 16 and this value. So others you can try it on your own. So this is the answer here. And then we go to another example. Okay, the last one is the X0 and XDFT0 using the central ordinates. Okay, on using the central ordinates, make sure it's only for the even sample. Even sample only. So X0 equal to 1 over 4. So this is the formula for the central ordinates. The summation for k equal to 0 up to 3. And then XDFTK. So XDFT is 4. Okay, and then you sum up, right? Sum up the XDFT. So you get plus with minus J2, plus with 0, and plus with 2J. So you will get 1. And also the XDFT0 is the summation 0 to 3 xn. Okay, then you get 1, 2, 1, 0. This one equal to 4. The last question is the question B. Prove that the summation of the xn square equal to 1 over n summation of the XDFT k square using the possible theorems. Okay, so we proved that the summation from n equal to 0 to 3, the xn square. Xn square, okay, so we have the 1 square plus 2 square plus 1 plus 0. So this will equivalent to 6. Whereas the XDFTK square is equal to CDFTK. Okay, so this will equivalent to 16, then negative 4, 0, and negative 4. So this CFDK is just now from the question 6, the periodic convolution. This is the answer from the periodic convolution. Okay, and then 1 over 4, this is based on the possible theorem x1 over n summation of the XDFTK square. Okay, so this is the summation k from 0 to 3, and then XDFTK square is equal to 1 over 16, 16 plus 4 plus with 4. Okay, why will I say that plus with 4? Okay, maybe I skip this part. Okay, plus with negative 4 modulus plus modulus negative 4, so equal to 6. Okay, divide by 4. 16 plus 8 divided by 4, so equal to 6. So this means that this value, summation of the xn square, is equal to 1 over 4 summation of XDFTK. So the value are the same. So this really show that the possible theorem is correct. Okay, so that's all for today, and see you again next time. Thank you very much.